سپاسگزارم از اعضای محترم هیئت مدیره و هیئت امنای مهندس و همیاران داوطلبان عزیز و شما شرکت کنندگان بزرگوار. من سینا فروزی هستم، عضو هیئت مدیره سازمان مهندس و هماهنگ کننده برنامه‌های تخصصی. با افتخار و سپاس و درود فراوان با آقای دکتر بهزاد حامدی برای پذیرفتن دعوت سازمان مهندس و سپاس از دکتر کوروش میرخانی، عضو هیئت امنای سازمان مهندس، برای این دعوت و هماهنگی با ایشان و سایر همکاران گرامی که این برنامه انجام شود. سپاس از خانم مهندس سپهری برای دیزاین پوستر این برنامه. اگر اجازه بفرمایید خیلی سریع یه توضیح بگم راجع به سازمان مهندس و 8 گروه تخصصیش، من جمله همین گروه مکانیکال زیر در واقع مدیریت آقای دکتر کوروش میرخانی. این 8 گروه AIIT، برق، مدیریت ساختمان، سیویل و مکانیکال، مواد هستند و کشاورزی و محیط زیست که برای هر کدوم از اینا ما یک گروه تخصصی تلگرام داریم که با کانتکت با ما میتونیم شما رو عضو این گروه ها بکنیم و در برنامه ها شرکت بفرمایید. یادآوری میکنم که برای اطلاعات بیشتر به www.mohandes.com هم مراجعه بفرمایید برای عضو شدن و برای اطلاعات بیشتر. خب، برنامه امشب A novel framework for modeling reconfigurable dynamic systems, theoretical focus, by our valued presenter Behzad Hamedi. Behzad Hamedi is a PhD candidate at Virginia Tech's Center for Tire Research, CENTIRE, expected to complete his degree in May 2025. He earned his Bachelor of Science and Master of Science in Mechanical Engineering from Isfahan University of Technology and Amir Kabir University of Technology, 1997, two of Iran's leading engineering institutions. His PhD research focuses on developing a novel framework for modeling reconfigurable and complex dynamic systems. Before joining Virginia Tech, Behzad worked at the Peugeot Group and the IKCO Research and Development Center, holding key roles such as chassis design engineer, technical project manager, and senior CAE engineer. His expertise include dynamic systems, control, vibration, structural analysis, multi-body dynamics modeling and simulation, vehicle dynamics, tire mechanics, and multi-physics. He has collaborated with academia, serving as an industry-invited lecturer and teaching courses in vehicle engineering and multi-body dynamics. At Virginia Tech, he was recognized as a top graduate student and has authored 15 research papers in the journals and conferences. Currently, he's teaching heat and mass transfer to undergraduate students at Virginia Tech. جناب مهندس حامدی، خواهشمندم آغاز بفرمایید.
ممنون. Hello everyone. Thank you very much for this time and opportunity, and also thank you so much for your introduction. I hope that this presentation will be insightful and attractive for everybody in the meeting. My presentation is focused on the novel framework for modeling the configurable dynamic systems with theoretical focus. So I start with, before starting to the presentation, just I want to mention that for more reference or more details, you can find my, you can go to my publications. So actually I published 6 papers in the journals for this research. So there's all of them are actually are open are available, and so you can access to them. And also, I will my presentation is actually a summary of these publications and the research. So let's do the start with the motivation. So actually, the key motivation for this research is to fill the gap for finding effective approximations for prediction of system vibrational characteristics. So when we have a complex system, dynamic systems, mostly the reconfigurable dynamic systems, as you can see in these pictures. A car is a good example for the reconfigurable dynamic systems because it's composed of the multiple subsystems, and for these subsystems we can reconfigure different alternatives and different options. For example, in the cars, in the body structures, you can have the sedan design concept, the crossover, hatchback, and in the powertrain, different configuration like ICE, EV or PHEV, and on the either dynamic systems like a steering system, you can have EPS, hydraulic steering systems, steering by wire systems, and also the other components. So this is a good example of complex dynamic system which is reconfigurable. So we are looking for a predictive approach that, of course, this is an approximation. It's not accurate approach. And we are going to find the radius order models that focus on just some measurements points or the degree of freedom. We are not degree of freedom of the system. We just selected some of them that is actually interested in terms of the measurement, in terms of the excitations, and we are going to determine this receptance functions and the vibrational characteristic on the subsystem individually. And then if we are going to find a generalized formulation, an algorithm that incorporate the all subsystems together. Because the subsystem measurement is much easier than the whole systems. And for us, this is a good opportunity to measure the response of the systems based on the subsystems characteristics. And also there are some generalized algorithm, but I could not find the algorithm that boasts rotational and translational degree of freedom for each points would be covered. And in this research, I have provided a more generalized algorithm to cover these requirements. And also, we are willing to find a hybrid modeling technique that deal with a different source of the data. For instance, one subsystems, receptance matrix can be measured by model tests, and other one by analytical and other numerical. So a hybrid technique and approach that incorporates the all subsystem informations, regardless of the source of data, would be one of the applying things in the dynamic modeling. So on the right side, you can see that, for example, a car decomposed on the three subsystems. One is the powertrain, another one is the steering system or the suspension, including the steering and braking system, and another one is the body structures. So, for example, powertrain, we can measure the receptance function or FRF using the finite element, and the others, for example, for the suspension systems from the FE or finite element or multi-body dynamics, and the upper body from the modal testing. So then we can apply this algorithm or this approach to find the overall assembly system, receptance function. And based on this approach that is a linear, if we apply the load and by knowing the receptance function for the system, we can find the response of the system based on the equation, simple equation or linear equation, x equals to h times f. So another application, one of the key application for this method is the receptance coupling method using frequency-based substructuring. That is a main focus for this research is the target cascading. So in the earliest stage of the development, you can see this is a V profile, common V profile that used for the industry, mostly for the automotive industry. So we start with the vehicle level and then we go to the subsystem decomposition on the subsystem level and do the design and then want to integrate the subsystem. So in this phase, in this early phase of the development, actually you sometimes you need to decompose a subsystem from the system, focus on just one subsystem, and assign some targets for that subsystem and to check the performance in the design process. And sometimes you need to combine some subsystems and integrate them to find the overall vehicle in the system level performance. So this technique is quite applicable for the target cascading process and is actually is effective approach in terms of the cost and time. On the right side, this is one example of the for this method, I mean the integration. So the whole vehicle actually decomposed onto two substructures. One is the upper body, and the other is a platform. So we assume that we count as a black box, that in the black box we have the DNA of this upper body, that is the receptance matrix, and the similar for the platform. So we actually then we integrate these two subsystems to find the overall vehicle response. So in the structural dynamics and the vehicle analysis, complex systems actually can be analyzed by dividing to the subsystem that we call substructures because they are more manageable and easier to measure. So the dynamic substructuring technique breakdowns to the three main categories. One is the physical domain, the modal domain, and the frequency domain. The physical domain is based on the time domain, and actually the model is based on the eigenvalue analysis, and the frequency domain, that is our focus, is based on the Fourier transform or FRF. And we mostly focus on this part, that is the frequency-based substructure method. So two of these methods is, the modal and the frequency-based. Both of these methods are model reduction, based on the model reductions. Model is a model reduction technique because actually it assumes that a system or substructures will be replaced by a limited number of the mode shapes. So that we call the mode truncations. Frequency-based substructuring, that is my focus here, is actually replacing or representing subsystems by a number of points that carries the DNA of the system, subsystems, that are the points of the interest that can be internal or in the connection points between the substructures. So when we define the subsystems, and we use the compatibility and the equilibrium conditions at the interface points to find the governing equations for the whole systems. So in this matrix, I'm going to compare the the modal technique and the frequency-based technique, that both are actually used as approximation methods for prediction of the system vibrational performance and characteristics. So the modal reduction approach for the modal technique, that also I mentioned CMS, because CMS is the component mode synthesis, is one of the main technique for the model that used based on the substructures and subsystems, is actually based on the mode truncation. The frequency-based substructuring is actually based on the condensing system to a necessary or required frequency, FRFs, or the receptance function for the key interface and the internal points. So we actually, our strategy here is the replacing of the subsystem by number of limited points in the interior, as interior or as interface points. So another assumption that is interested to mention is that, okay, then when we work with a model, we assume the mode orthogonality in most cases. This mode orthogonality would be valid in the low and mid frequency range. When the damping effects is quite simple, and we can assume that this is a proportional damping or Rayleigh damping, or I would say that is weak damping. But when we have in the high frequency range, I mean, the modal orthogonality may not be valid, and actually we will involve the damping, complex damping effects. But in the frequency-based substructuring, there is no inherent in the limitation on damping matrix. So actually, there is not any limitation inherently to the modeling technique. Both methodology used based on the linear assumption and also the quasi-static systems. Frequency range is, as I mentioned, model is focused mostly for the low and mid frequency range. But this methodology that I'm focusing on that for, based on the FES, is applicable from the low to high frequency, despite that we are in a linear domain and the linear based on the linear assumption. So the equations that we can remember from the vibration course, x equal to hf, that the x is the response, h is the receptance function, and this f is the excitation. And the h can be calculated from this equation, h is the receptance functions. So in the model technique, we calculate the h as from this equation, that this equation, the assumptions is based on the assumption of the mode orthogonality. So the H, the receptance matrix, can be calculated from these equations, and we can talk about that later. So this slide shows the roadmap and the flow chart, how we can determine the receptance of the assembly system or entire system based on the individual subsystems or substructures. So the first step, we start with identifying the points of interest, which points are required to measure or focus on that, on the subsystems, and then define the partitioning strategy. So how many subsystems you are going to focus on that, 2 subsystems, or you want to decompose the system to the higher level of the subsystems. So it actually depends on your availability for the subsystems, the information, and the data that you have. So the next point is actually is focused on the concept of the connection between the subsystems, because the subsystems sometimes are connected through the single points, sometimes multi-points, and sometimes there's actual flexible points. So we have the bushing, we have mounting in the connection points. So we need to define which connections and how we can model this connection by the rigid assumption or with a flexible bush. bushing or mounting. And the next step is focus on the generalized coordinates, how many degree of freedom we can consider for these points. Is it translational or rotational, or we have combination of the both? Depends on your loading and the physics of the dynamic systems. And the next step is actually determine the subsystem resistance matrix. So you should actually define that each subsystem data would be collected from the test, which one is based on numerical, and which one sometimes is the simple subsystems, and we can use the analytical equation by resistance matrix. So the next step is the filtering of the FRF or the receptance, if it would be based on the measurement. Sometimes the measured data is noisy and you need to filter to have a polished data for the receptance matrix. And then the next step is just focus on the selection of a methodology for the coupling of the substructures based on the assumption and your requirements. And then finally, determining the receptance matrix and the component of the receptance matrix based on the algorithm governed in the integration of the subsystems. So this slide just is a fundamental recall to describe the FRF and receptance matrix. So with assumption of a single degree of freedom, so we could obtain to the H receptance function as it is this complex function, and then we can determine the magnitude and also the phase angles. And on the right side, you can see that this is a graph of the receptance magnitude. So based on the frequency omega, and then so the FRF or the receptance matrix is actually determined by the modal test or modal analysis, experimentally or numerically. So in fact, this FRF, our receptance matrix, is great. A clear insights into the dynamic behavior across a range of frequencies for a system, and used as an indicator for health monitoring of the system to check that the system is under degradations or damage. And that's actually because it monitors the change in the FRF over time. So the change of the FRF over time is a good indicator to check that the system is healthy or not, dynamic systems. So this actually, this slide, I'm just going to illustrate that the 2 degree of freedom, how we can describe a 2 degree of freedom based on the matrix of the receptance. So the X1, if you have 2 points, X1 and X2, so we have, if you apply 2 excitation, F1 and F2, and we can calculate X1 and X2 based on this matrix form. So H1 means that the component of the receptance that can be obtained by the excitation at the point 1, applying the F1 as excitation and measuring the displacement X1 in the same point. So H12 means that applying the force at the point 2 and measuring the response at point X1. So in the case that we have actually the same number of the excitation and the measurements, so that would be this equation, the F can be calculated from the inverse of the H times X. But in some cases that the number of excitation and the measurements are not the same, so in that case, we can replace the inverse by the pseudo-inverse matrix. So in the left side, we can have this equation for the n number of degree of freedom systems, n degree of freedom systems. So we can write the same equation, similar equation for the n degree of freedom systems. For more straightforward description, when we have the internal and the connection points in the dynamic systems, we can use this form of the equation, and the I is internal, and the C describe the connection degree of connection points on connection degree of freedom. So as a simplest case, we start with a subsystem, with a system AB that is including two subsystems A and B. So in general case, its subsystem has own internal degree of freedom that we want to measure or excite. And also we have the connection degree of freedom. So in the decoupled condition, because we want to measure the subsystem individually, subsystem A can be measured, the receptance matrix can be measured by the test or the calculation, numerical calculations. And also similarly for the B, if we have both the degree of freedom or the internal as A and the C is the connection for the A, and the B is the internal degree of freedom for the B. So the Z is here is a dynamic stiffness that is inverse of the receptance matrix. So let's consider this simple case that only connection degree of freedom we consider without any internal degree of freedom. So only we assume that we just focus on the connection points in the interface. So in this condition, we ignore the internal degree of freedom for simplicity, and in the decoupled condition, so the governing equations for each subsystem would be like that. And when we consider the boundary conditions as equilibrium and compatibility equations on these connection points, we can write this equation, the boundary condition, like these equations. So we assume that this is a rigid connection, so the same displacement at the connection points between the AB, the assembly, and also between the connection, the same point on the substructure A and on the same points on the substructure B. So based on the continuity equation, so if we combine this all in equation, we can reach to these equations. So by canceling out the x from both sides, so we can reach to these equations. So in the simple case that only we have the connection degree of freedom, or we ignore the internal degree of freedom, we have a relationship between the receptance matrix of the individual substructures and the assembled system. So in that case also, we can find the equation of the motions with this equation. So x is equals to h times f. So this is a simple case that we just have the connection degree of freedom, or the connection points. So this example, this approach that we have only to focus on the system, including two substructure or subsystems, with just focusing on the interface degree of freedom or interface connections is in these examples. So the underframe is a subsystem A, and the upper body is the subsystem B. So we want to calculate the receptance matrix of the overall system when we have the assembly of the subsystem A and B together. So we can find the subsystem A H function or receptance matrix from tests or numerical FEA or the multivariate dynamic simulations, excite these connection points, and measure the displacement at the same connection points to find the receptance matrix. And then similarly, we can do on the body structure, on the connection points, to find the HC at the connection points. And then we can integrate, we can use a coupling method, similar these equations to find the receptance matrix for the assembled condition, or assembled dynamic systems. So here the HCC is it can be a single data or a single number or a matrix. So here, if we have one connection, so that will be only one single data. But if we have the multiple connection like here, so the HCC would be a matrix. So if you consider the both internal and the connection degree of freedom, but we have the AB, still we have the two substructures assembled to create the AB system. But consider the more complex cases that we are interested also in some points on inside of the substructures. And then this equation is not valid anymore, because this is only focus on the connection degree of freedom. And then we can prove that in this case we have a more complex form of the equations that define that determine the receptance of the AB assembled based on the receptance components of the individual substructures. So this methodology or this equation first developed by Jet Munson and published in 1988. So here, actually, I want to interpret the definition of the receptance component, HAB, I mean, the physically. So the HAB from this equation, let's extract HAB between the points of the A and B. The points A here and the points B is internal points located in this substructure B. So if we want to find this component from the other components, so that would be, this is the zero, and then this would be a manipulation of this term and this term and this term. So actually, we can reach to this equation if we want to find this component. So in this term, actually, this middle term is it describes the receptance of the connection points. So if there is no spring or there is no flexible mounting in the connection points, so this is the case. And the HACA is actually determines from the individual measurement on substructure A by excitation of the point C and the measuring of the internal points A give you the HAC on the substructure A. And similarly for the HCB, B is actually the excitation. We apply the force or excitation at the point B and they measure the response at the interior point of the we apply the excitation force at the internal points of the B, and they measure the force measure the displacement at the connection point. We also can prove that we have the symmetric, so HCB is equal to HBC. So this is the physical interpretations behind these components of the assembly and the components of the receptance for the individual substructures. So in case of that, we have the flexible mounting in the connection points. So the stiffness of this connection or the flexibility will be appear here as the term K minus K inverse and added to the receptance at these points, and this flexibility will be added. So as a simple case study, we consider a 2 degree of freedom dynamic system that the both ends are fixed or are constraints. So if in this case we can apply the substructuring method and then decompose these systems to two subsystems, and that actually that are connected with a spring. So we have flexible connections. So for this simple case, that is this based on the lump mass systems and with assumption of the low frequency range, there is a small error between the model technique. If we solve this equation using model and the frequency-based substructuring, I mean receptors coupling based on the FBS, so it's quite the error is quite small, and we have a good correlation, and it's quite identical. So this is the results. So actually, I compare the receptance coupling based on the FBS, frequency-based substructuring, the model technique, and the direct. Direct is the exact solutions that can, for the system, easily can be determined using the applying the governing equation based on the Newton law or Lagrangian formulations. So here in the graphs, you can see that the error between the model and the exact solutions. And on the right side, you can see the error between the RCFBS and the exact solutions. So the error is quite small, and for this case, the results are quite identical. But we can show later that if the dynamic system is more complex, and the flexibility of the substructure involved, so this deviation or the gap will be higher. So in this case study, I consider the quarter models, and then we apply two substructuring schemes. The first scheme is based on the minimal segmentation approach. That's okay. We just focus on these two substructurings. So we split or decompose the systems from here. We cut the systems from here, and then we converted this system to the two individual substructures, and we applied the similar equations that we talk about that to find the receptance of the whole system. So here we use the Z. The Z is the dynamic systems. So the third one, third substructuring scheme is based on the more detailed or more systematic element partitioning. So the partitioning is based on the elements, so element-based substructuring, and all of this situation. That the first one is actually the deriving the equations based on the analytical approach, and we just calculated the H11, that is the receptance component of the matrix, by applying that describes the excitation from this excitation, this point, the point Z1, and the measuring the displacement at the same point. So if we can calculate from the analytical approach, we can find the H11 from this equation. And if we apply the substructuring techniques, we can find the similar equations, and actually see that for this case, that is a simple case study, all three options are identical. So the important, the great things is that you can find the natural frequency of the system without measuring the model test on the whole system, by just measuring the individual subsystems receptance, because you reach to these equations. So this equation is the H11, that is describes the displacement over the force. Displacement is Z1 over the F1. So if we want to find the frequency, natural frequency, it means that the displacement in this frequency should goes to infinity. So it means that the dominator goes to the zero. So from the receptance components, you are able to find the characteristic equations that can drive the natural frequency. So this is one of the beauty of this equation, this approach, that indirectly can calculate the natural frequency or drive the characteristic equation for dynamic systems. So I published these results and my research in these papers, and you can go for the more details about what I discuss and the application on the automotive industry as a paper that is including much more details or what I just show in the one slide. So another application for this methodology would be tire characteristic using the coupling and decoupling techniques based on this method. So for instance, you want to calculate or to measure the full vehicle receptance matrix, and then based on that measure the response. So you can do it based on the measurement of the substructure A, that is the vehicle without tires, and the substructure B measurement, that is its own tire. So we can focus on the measurement of the subsystems individually. Tire, we can measure the tire because it's easier. We can measure the upper body, or we can have the data of the upper body without tires, and then we can use the coupling technique and the receptance coupling technique, and use this equation to find the coupling, the coupled system receptance matrix based on the individual subsystems receptance matrix. And sometimes you are interested to measure one of the subsystem. For example, you have the data, from the modal data that modal analysis that you have performed on the full vehicle, you have the receptance matrix. You also have the receptance matrix of the car without tires, and by this decoupling technique, and the B can be derived from the coupling of the AB and minus A, because the AB minus A give the B properties. And then so the receptance, I mean the RCFBS is flexible coupling and the coupling. So it depends on the case. So we can have this flexibility to use whether you are interested in coupling and to find the integrated response between the multiple subsystem, or just you want to focus on one subsystem from the system. So the question is that, okay, how we can another challenge is actually, I would say, that measurement of in the disassembled case, for example, the tire. The question is that, okay, if we want to calculate the receptance matrix for the tires, so in the case that is how we can be ensured that is the representative of the car, because the tire, when the tire is fitted in the car, so that would be under preload. So, but when we disassemble the tires, so we release the preload. So if we want to measure the receptance matrix for the tires or also the cars, so we should apply the preload to create the same static condition for the tires. So this is the more detail of what I mentioned, how we can, which steps I should take to apply the preload. So for instance, we should consider the spring, the dummy springs at the attachment points, and apply the forces, and then compress the springs and the belting mechanism to hold the body and to hold the tires in the correct right heights and the correct preload conditions, and then measurement of the receptance matrix. Okay, so this is the slide describing the GRC-FBS method. So this is the first generalized receptance coupling technique using of the frequency-based substructuring that we call it Jet-Monson algorithm. Jetmonson started with integration of the two substructures, and then extended this equation to cover the multiple substructures. So if we have an n number of substructures, so the equation will be changed to this general form. So in this equation, so the H couple is the H of the assembly. So the M matrix is introduced here as a Boolean mapping matrix, which connects the interface and the subsystems together. Because when we have multiple substructures, so we have the multiple connection points. So we need to define define a baselines or as a mapping matrix that connects the interface and the subsystems together. So for driving this equation, the graph theory was used. And so the Boolean mapping matrix derived based on the graph theory. And the MS here is the component of the mapping matrix, the Boolean mapping matrix for each subsystems to describe the all interfaces. The alpha and the gamma is the internal and the interface degree of freedom, and the H alpha alpha is the partition receptance matrix for the substructures before applying the integration or before applying of the forces in the connection. So this is in the disassembled condition. And the H gamma gamma is the receptance matrix for the connection points, and the H describes the substructures. So this is the more general formulation. So the second approach for the second methodology that's used as a generalized receptance coupling, that is the LMFBS, that is based on the Lagrange multipliers, is a Lagrange multipliers approach. So I don't go to the detail of the driving the equations, but in this method, actually we defined Lagrange multipliers to determine the internal forces in the connection points. So based on applying the compatibility equations on the interfaces and defining the internal forces in the connection as a function of the Lagrange multipliers, and then apply the insert or plug in the equations of the motions, and then we can reach to this equation that give you the H of the assembled system or the coupled system based on the H, that is the H is in the condition of the disassemble or the decouple conditions, but this H covers all subsystems, and the B is the Boolean matrix that is used from derived from these equations from the compatibility, because for these cases that okay, there is a relation between the degree of freedom in the connections, so the B matrix can be calculated from this interface or the connection in the between the degree of freedom at the interfaces. So L is actual localization or localized Boolean matrix, and the B is we call it the sign Boolean matrix. Is similar to the previous method that we called it by M matrix. So the lambda is into Lagrange multipliers, and one of the advantage of this method is not only you can reach to the receptance function, receptance matrix of the whole system, but also you can find the internal force in the connection. So if you can find the lambda, and you can determine the internal forces in the connection between the substructures. Okay, so the second example, the next example is the applying the radius order model technique for the electric motor noise study. So if this is the Tesla model chassis, so we can use this methodology to derive a radius order models. So if we have electric motor, we have the electric motor resistance matrix by testing, and then we have the mounting, the main mounting or data or the stiffness and the subframe data by the test or the FEA, and also this is the trim body. That is actually the trim body is not here, but is we assume that the connected this struts of dampers connected to the trim body. So we actually we can define the three substructures for representing of this the electric chassis systems by the three substructure A and B and C. So that actually this is the coupling graph between the A and B and C. That the A is the underbody, the A substructure is underbody, and we consider internal degree of freedom for the interior points, and also we consider the connection points for the substructure A. And so this could be A, or I mentioned here the F excitation. So F excitation, so A would be the substructure, A would be electric motor, would be the electric motor, and the B would be subframe, and the C actually would be trim body. So the electric motor will provide excitation. So this is the excitation source. And so the A is the electric motor substructures. And for the B, actually, that is the subframe. So we can consider the both interface and the connection points and also the internal points. So we can consider a points of the measurement on the substructure B, and there are connection points between the in one side connected to the body structures, connected to the electric motors, and the other there are another connection between the body structures. So through the mounting. So this actually can be represented. So this is the schematic of the substructuring scheme, and this is the how the coupling between the three substructure R's. So I actually I published this. The whole deriving the equations for this case, and the more details talk about how we can derive the equations and use this technique to derive the response of the system. Actually, in this paper, so you can, if you are interested, you can reach to this equation. So to this paper, this is the very general formulations for this type of example. So the alpha is the degree of freedom at the points of the interest and connection points. So we have two connection points, C1 and C2. So H alpha is the receptance matrix before coupling. So it covers the three subsystems receptance. So you can see here the before coupling, the H alpha, that is the receptance before coupling, and H alpha gamma is the receptance between the alpha and the gamma, that the gamma is the connection points. So, and the M is the Boolean matrix that is based on, that can calculate, that drive based on the graph theory or the graph schematic that describe the connection points and how the connection interfaces are between the interface and the substructures. And also the M MA and the MB and MC is for each substructures that drives from this matrix, from this M. So the first row is for the A, second row for the B matrix for the B substructure, and the third row is for the C substructures. And then we can couple them, and we can use this generalized formulation to drive the coupled receptance of the whole systems. So in this slides, I just use the second method. I mean the Lagrange multipliers method using the FBS, frequency-based substructuring. So this also can give the same results if we use this methodology or second algorithm. So we can reach to the similar response for the H matrix for the whole system. So now just I want to talk about the extending generalized explicit terms. So in my research, I was working to develop more generalized form of the equations. So I developed this type of the equations that we can integrate both translational and rotational degree of freedom in more explicit form. And that would be actually quite effective for capturing the dynamic of the flexible structures and when we have the complex loading situations. And also, I used for determining the receptance matrix for the flexible bodies. I use the Euler-Bernoulli beam theory and to determine in the to determine the yeah, this is the paper that I published that is including all details, how we can determine this, how I develop these explicit terms, more equations, more generalized form of the equation that actually govern this type of the, I mean, in general, generalized form of the receptance matrix. So this is the detail of the equations that I derive for more general case of this. So this is the examples or the case study that I used and in this case. So as a one case study, just applied my methodology. Just I consider the simple cases because the simple cases that is based on the two beam elements or two flexible body with the beam elements. We have both rotation and the translational degree of freedom. And because one of them is the cantilever beam, the another is free beam. So we can calculate the each substructure individually using the analytical equation based on the Euler-Bernoulli theory. So that was the reason that I used the simpler case. So we can substitute each one as a substructure. So this is a substructure A. This is a substructure B. We have this in this connection. We have 2 degrees of freedom. We have both translational and the rotational. And when we find the assembled receptance matrix, so in the different cases, so this is a graph of this graph compare the 3 graphs H11, H12, H22. That is based on the different excitations. So for example, H11 is excitation. So you apply the force at the point of the A, I mean in the y in this simple force in the y1, and the measure the y1 the response, and this would give you h11, and h12 can be calculated by applying the moment a torque at a point at the degree of freedom, this degree of freedom. Uh, and also they measure the theta 1, and also similarly for H22. So when we compare these three graphs, all the peaks are similar. So that was the inherently expected, because the assembly system receptance components aligns actually with the natural frequency of the system, of the overall systems, because it doesn't matter which kind of excitation you apply on the dynamic systems. So regardless of the excitation, you reach to the same results and the same frequency, natural frequency, because this is the natural frequency is the property in intrinsic properties of the dynamic systems. So in some in this graph also you can see that in this graph you can see that I have compared my methodology GRC-FPS with the numerical FEA, and you can see that there is a good correlation between the two methods. This is for the H theta 1 theta 1 receptance component that is based on the rotational measurement at the tip, at this tip point, due to the couple that apply to this. So if you measure this magnitude of the receptance functions, the receptance components of the H theta 1 theta 1 on the assembly, and compare the finite element method, so we have a good correlation. And also for y111, so we apply the force at the tip and they measure the displacement, and you can reach good correlations. So for the cross receptance components, so we have the shift in the higher frequency. So we have the gap here, so we can talk later about that. So another case study, we just consider a flexible body with a rigid body, so a rigid wheel. So I wanted to know how is the dynamics of these systems. So in this case, also we had the similar phenomenon that okay, this natural frequencies is independent of the excitations. So we have H11, H12, H22. If we calculate on the system level, and then we can reach to the same peak and the same natural frequency that of course we expected. And but when we come to this to compare the for example H theta 2 on the assembly, this is the component of the receptance matrix in the assemble. So if we compare the magnitude between the two methodology, GRC-FPS and numerical FEA, so we have a good correlation in up to 2000 Hertz. But beyond that, so we have a gap. So we have a shift of the frequency, the peak of the natural frequency. So the trend is similar, but of course for another component H2 Y2 also we have this shift in the higher the frequency beyond 2000 Hertz. So there is a good agreement between the two methods in the first dominant mode beyond the 2000 Hertz. So the rigid components influence increase and affecting the accuracy. So we assume that one of the source of this gap base depends on our assumption. We use the Euler-Bernoulli theory, Euler-Beam theory, because it's assumed in negligible shear deformation and rotational, and also ignore rotational inertia. So, and in actually this theory is less valid in the higher frequency, and if we want to be more accurate and bring the effects of the rotational inertia and the shear deformation. So for that would be important for high frequency. So we need to use the Timoshenko beam theory. So anyhow, in case that I use the Euler beam theory, and also I use a simplified finite element modeling technique, so we could reach a good correlation of the error is around 4%. And if you want to improve that, is possible. So in the FEA, I can use the more refined mesh, the mesh refinement. We can apply the higher order elements, I mean the quadratic instead of linear, and also considering the material damping. So I also can reach the good correlation if using the Timoshenko beam theory instead of the Euler beam theory to capturing better high frequency inertia effect and the shear deformations. So this is another case study that this is for first time that applied this technique to derive the dynamic of the whole vehicle using the generalized receptance coupling FPS, using the frequency-based substructuring technique. So this is for use for the tire characteristics. Sometimes you need to supplier wants to evaluate different type of the tires on the vehicle vibrations. So in that case, you have these substructures. You can measure the substructures receptance. I mean the body structures below tires, and then you can you can integrate the different tires receptance and to find the overall receptance matrix. So the detail of that is actually is represented in this paper. So in this paper, so this is actually the detail of how we can develop this theoretical framework and methodology for prediction of the tire characteristic. So this is the if you are interested, you can go to this paper and study that for the that is actually published in Journal of Vibration Engineering and Technology this year. So for solving this problem using this technique, I mean GRCFBS, we have we have five substructures. The B is the body structure as a base substructures. We have add-on substructures or A1, A2, A3, A4 as a tire substructures. So I consider the four different individual substructures because in the general case, the tire pressures on the front and rear are different. So the vibrational characteristic of the front and rear tires are not same. So that's the reason that I consider as a separate and individual substructures. So the degree of freedom, so we have interface degree of freedom and also integral degree of freedom. So X1, X2, X3 are the interface degree of freedom that we call it as a C. So this is the interface degree of freedom, and also I consider integral degree of freedom not on the tire, just on the body structures as X5, because you are interested to measure the vibration at one point on the body structures, and you want to, for example, record the noise on the microphone on the that's installed on this point, and so I assume that there is no internal degree of freedom on the tire. So this is actually the coupling that I used for this problem. I use a multi-steps scheme. So in the first step, I assembled because I wanted to use the governing equation for the assembling of the two substructures. So I started to assemble the A1, the first tire, front left-hand tires as A1, and assemble with the body structures. And then this is the scheme of the substructures, that the substructure B is including of the four five I mean the 5 degree of freedoms, or 5 general coordinates. We have the x1, x2, x3 is the connection degree of freedom, and the 1 is the x5 is the degree of freedom, that is the interior. So when we assemble these two substructures, and then we can consider these two as a one substructures, and then assemble to the second tires. And also the third step is considering the previous step as one substructures and assemble to the tire A3. And then as a last step, so we can assemble the substructure A4 to the substructure B, A1, A2, A3. So this is the process for the deriving the equations. So the beauty of this method is the dramatically the number of the measurements and the measurements to develop the full vehicle for full vibrational model will be decreased. So this is one of the beauty for this method. So for this case, we just need to measure only 5 elements and disassemble substructures. So for the body structures, so we need to measure B11, H11B, H21 on the B, H31, H41, H51. So we need to excite point 1, interface point 1, x1, and then measure the displacement at the x1, x2, x3, x4 to calculate these resistance components for the body structures, for the body substructures, and also for the substructure A1, just measure H11. We now ignore the interior degree of freedom. We just consider the connections. So we apply on the dismounted tire, A1 tire, we just apply excitation at the point of X1, the same point that is in the connection point, but is on the A1, in the tire A1, and the measure displacement at the same point, and that give you the H11A1. And based on this measurement, these 5 elements measurements, so in the next point, in the next steps, you can use the equations governing for the coupling of two substructures. And this in this equation, I can find this component H11, H21, H31, H41, H51 on the BA1. This is for the first two substructures assembly. And then there are some other components, and the rest of the components, 10 set of the elements can be determined from the chain rule. So we can use the chain rule to determine this number of this component level, because the matrix of the H is a 4 by 4 order. So we have 25 elements. So the 5 elements can be calculated from here. 10 elements can be calculated indirectly. There is no need to measure. Indirectly can be determined using the chain rule. And then the 10 elements can be determined through the symmetry law. So because we have the symmetry for the receptance matrix, so by measuring of just 5 elements, so you can determine the BA1 H receptance matrix for the coupling of the B substructure B and A1, just the first two substructures, and then we can continue the similar approach for the assembly of BA1 to A2. and BA1, A2 to A3, and also to go to the complete assembly of the recipients for the assembly of the car, just by the starting of just 5 measurements. By just 5 measurements, 5 elements of the recipients on the disassembled condition, on the disassembled, dismounted condition, you are able to catch the recipients of the whole vehicle from this approach. So this is another concept or another procedure that is there is a possibility to assemble in one step, instead of single step, assemble the 4 tires to the body structure. So this is another scheme for the integrations. So I will not go through that because it takes a lot of time to discuss about that. But uh, this is the case that is a similar case, but with the only difference is that we consider the integral degree of freedom for tires. So this is a similar case, but we just consider A1, A2, A3, A4 as interior degree of freedom or interior points on the tires. So each tires has 2 points of the interest. One is the connection, and the one is the internal points, because you need to measure something on the tires. You want to apply to excite these points on the tires, the center of the points in the tire. So you need to assign this point. You need to consider this external to additional points in the as interior. So I can use for this case, I can use the general formulation, general as GRC FBS. That is a more general case. We use the Boolean matrix. We develop the Boolean matrix from this Boolean matrix actually is give you how do we have the relationship between the different substructure, because we have BA1, A2, A3, A4 substructures, and how these substructures are coupled with these have interface or are working together or are in contact with each other through the interface. So C1, C2, C3, C4 are 4 connection area. So the M matrix components are the -1 and only -1, +1, and 0. So it depends on the direction of the direction that you consider for the coupling graph, the connection. I mean the direction for the vibration. So for example, here the vibration comes from the tires to the body structure. So this is a reason that we consider the direction for that. So this point to consider positive, living point is positive, and entry point is negative. And for example, for the C4, the C4 is the connection between the A4 and the B. So this is a C4 is the connection between the B and the A4. So you can see here that we have the -1 and the +1, because the C4 is just describing the connection between the B and A4, and the rest are 0 because there is no connection or there is no interface between the other substructures with this connection zone. And so the H and the M and the rest of the matrix can be calculated from this approach. So another example is that another case study is the development of the reduced order car model for NVHS study using GRC FBS. I use this methodology for applying this technique to derive the recipient's matrix of the half car model using the substructure techniques, because This is actually is quite new, so we could not see before that this approach used, and that can be extended to the full vehicle. So, but this is just half car. So we have three substructures. One is substructure is a sprung mass, upper body, and we have two substructures for the front suspension and rear suspension. But also, I consider the B1 and B2, two front and rear substructure, as a unique substructures, because the front and rear suspension don't have interface to each other, so they are decoupled. So we can consider the substructure B as a combination of the B1 and B2. So for the detail of this if you're interested, you can go to these papers, and all details are inside of these papers. So for this case, so what I did, I compare exact solution, because this is a simple model, and we can derive the equation using Lagrangian method or Newtonian methods. So we can use exact solution, and we can reach to this equation. We can derive the equation of the motions. We have 4 degrees of freedom, U1, U2, U3, U4, because we consider 2 degrees of, we consider 2 degrees of freedom was U1 is this point, and U2 is this degree of freedom for this point. Instead of considering the center of gravity Y and center of gravity degree of freedom as a translational, as a bounce and as a pitch, I just consider the U1, U2 is easier for using these equations. So, and the U1, U3, and U4 is degree of freedom for the translational bonds of the front and rear unsprung mass. So in the direct method exact solution, we can easily derive the equation of the motion as a U equals to HF. F1, F2, F3, F4 is the excitation force. U1, U2, U3, U4 is the displacements in the general coordinates, or in the degree of freedom, and the H can calculate from this equation. So M matrix and C matrix and K matrix can be derived from the exact solution, and then you can find this equation of the motion, and the resistance of the whole assembly can be derived from this equation. So this is the equation that can drive for determining the resistance of the whole systems if you use the exact solution. And another method is determinant-based method. So the component of the H component of H matrix can be derived from this equation, that the delta is similar to these equations. And also the modal analysis, I use also the modal technique to derive the resistance matrix based on this equation. So this is the HIG is the resistance component of the H matrix using the modal analysis. So phi IR, phi JR is the mode shapes, and the N is the degree of N is the number of modes that you consider based on the mode truncation method. So this is the phi is a mode shape. I mean the eigenvectors, that is a normalized eigenvectors. So the another technique that is my focus is that for the resistance matrix, resistance coupling using the GFR frequency-based substructure method. So this is a very general formulations. So this is the equations. We have two redundant degree of freedom, because the redundancy is due to the connection points. Because UA1, U8, U1A, U2A is in the same point, but in the two different substructures. So this is the reason that we have two additional degree of freedom, but they are redundant, and So that actually that would be similar, I mean, in the response. So the Bay matrix can be derived from the interface equations, because the interface equation is quite rigid. So the displacement between the U to A, between the points to A in the substructure A, and the U1 B in the substructure B is similar. So this is the continuity or compatibility equations, just because this derives based on this, that the displacement in the connection points between two substructures are similar, and this can leads to the driving these B matrix. And also the H is the matrix before coupling. So this is the decoupling matrix for the B. So the some terms here is zero because there is no coupling between the front and rear suspension substructures. So I consider the substructuring or the coupling between the two substructure. One is the B, that is the including of the that's covering the B1 substructure and B2, and another one is the substructure A. So this is the coupling of the two substructures. So if we derive the and plot the results, so and compare the different methodology, so the exact solutions, the model, and the frequency-based substructuring. I also consider here the FBS and the LMFBS and Jet-Monsen FBS, because I wanted to compare two different algorithms that we talk about. We have two different algorithms for the reduced order model development based on the frequency-based substructuring. So I wanted to compare this also to two methods. So we quite have the good correlations between these methodologies. So the results are quite aligned between these methods. So we can capture the natural frequency, the peaks, also on the magnitude. So we have a good correlation. We on the phase angle, we have the receptance phase angle, in the receptance magnitudes. So we have good correlations. So these are some components of the receptance matrix for the assembled, based on in terms of the individual receptance components of the substructures. So as a general synthesis for analyzing of the dynamic behavior for this problem, I mean the half car model. So we reach a good correlation, I mean, in the resonance frequency. So we we more or less reach to the similar value for the natural frequency, and so we could obtain the dynamic of the peak on the magnitude, I mean the resonance points, and also anti-resonance. So because both behavior actually are important. So the anti-resonance points and also the resonance points, and also in the phase plot we could capture a good correlation in the behavior. So we could see the phase transitions -180 degree near resonance, and also near the anti-resonance we could see the phase shift back to the zero. So actually this is what we expected. So also we checked reciprocity situation, and also we measured for the verification of the results. We measure the component of H21 and H12, and similarly H21 and H42, and we could see that the results are same. So we could see that there is symmetric law between the symmetry can be held between these components. So this is the general results. Uh, the proximity of two frequencies, that actually two frequencies, we could observe a phase discrepancy, observing the modal approach, because the modal approach could not get the behavior accurately when we compare the results, because two natural frequencies are close. 9.2 and 9.3 front and rear suspension bounce frequency are very close. So what we could see that the FPS method, I mean the general FPS method, GRC FPS could catch the behavior when I compare with the exact solution. But in the model, actually, we could see that there is a discrepancy, and there is a shift in the proximity, the frequency close to this frequency. So I come to this conclusion, and this results also discussed in the paper that I refer to, that the modal method struggles with to differentiating the modes that are very close, and that would comes to the phase inaccuracy, a slight phase inaccuracy in the results. So another case study for as a dynamic structures, we can decompose a system ABC by three subsystem A and B and C. So the one example would be under frame or under structure for the vehicle. So we can consider these reduced order models for these underbody structures that is encompassed the three substructures. So we have we have the translational and rotational on the substructures and then the structures. So we can consider this is a scheme of the substructures. In the connection points, we have the both translation and rotations. So this is another descriptions for the substructure scheme. We have three. So I consider the three beam elements for each subsystems as a beam elements to derive the to apply the Euler-Bernoulli theory to find the receptance functions in an analytical form, because we didn't measure experimentally. So when we compare the results, so we came to the good correlations between the methodology, between the model and GRC FPS and the numerical finite element method. So you can see that the one verification of the results was, okay, we could compare the receptance components, magnitude versus the frequency, in the different excitation. But in the different excitation, we could reach to the same behavior. Of course, the magnitude, of course, the graphs would be different, but the peak of the graphs would be similar. So that was what we expected from the physics of the problem, from the physics, and the natural frequencies are independent of the excitation. So that actually verified the results. And also there is a good correlation between the receptance components. Also, we use we compare the H21 and H12 to see that, okay, the results are quite same, and we can see that the symmetric law is held, and that's the one of things that we can use as a validation of the results, on verification of the results. So As a summary, the major contribution of this research is, okay, this is for general reconfigurable dynamic systems that we can use in the diverse range of the fields like robotics, aerospace, manufacturing. We can develop a generalized methodology for coupling of the multiple subsystems with the different kind of the interfaces in the complex dynamic system domain. This methodology can enhance our understanding to how vibration and mobility transfer through the subsystem and interfaces. And also that would be an effective methodology for capturing dynamics of unknown subsystems through the complex dynamic systems. In an automotive context, we can develop a full vehicle model with multiple subsystems, not limited to 2 or 3 subsystems. In general case, if you are interested to consider subsystems like the powertrain, like the suspensions individually, or you wanted to focus in more detail to the multiple substructures with different interfaces, so you can use this technique and develop the effective coupling methods for the analyzing the road noise in the early development. So this one of the application is for the road noise analysis and tire characterization. So also we can use this methodology for target cascading in the early stage of the product development, as also it was discussed. So future work is that, okay, there are some area that we can work as in the future, modeling of the joints with considering the preload. So develop methodology to account the preload effects, capturing the influence on the system dynamics and stability. So apply the approach for developing of the radius order model for the nonlinear dynamic systems. So what we discussed is based on the dynamic system, linear dynamic system, but these are the new area that we can focus on that. So applying this approach for the robotic application to find the effective radius order models, and also the perform validation on the physical cars, that will be what we can do as a future work. So thank you very much for all your attention. So I would be happy if you have any questions.